Hi, this is Roger from Kanka Labs with the next teardown of my collection of 4.5-digit multimeters in preparation of a forthcoming video. This time it's the Extech MM570A, which I bought in the early 2010s. And what I didn't know during the date of purchase is that this is in fact a rebranded Brymen BM859 and also sold as a Greenlee DM860, an M-Probe AM160A and a Sanwa PC7000. So the original is a Brymen, but sold under at least 5 different rebranded designations. And you can even buy it today. There's even an updated version. So what interests me is, just as with the last teardown, how is the protection inside, and can we gain any insight into the used ICs or circuit topology, which is not obvious from the specs. So let's start to open this up. So let's start with taking off the rubber holster, and then we have, here you can see this is the port for the infrared data transmission for data logging. So let's see what screws we all have to turn loose to get inside. So these are not threaded. So these are obviously self-tapping screws. And what I knew beforehand, they are little rubber O-rings or seals. It looks like that they serve the purpose to really seal the case, for either making it kind of waterproof, or in case of failure that no flames or smoke can escape from the inside. So we have a separate battery case, which is a kind of a separate chamber, probably also to make this waterproof from the outside and smoke or flame proof from what can come from the inside. And 2 further screws Here we again have these rubber O-rings. So now we should be able to open this up, but I probably need my metal spudgers. No, it just come off this way. Aha. Okay, we have an additional rubber seal, and you can see the construction is kind of well, it's not double walled. Okay, here comes the interesting part. Let's increase the zoom a little bit. So you can see there's a whole armada of protection components, and because this meter is not only Cat 3, as you can read here, but also Cat 4 rated, there has to be a lot of attention to details concerning the protections of the meter itself and of course of your personal safety. And so if we take a look, the first thing that gets your attention are, of course, these heavy HRC fuses protecting the milliamps and the amps range. I've made a separate video about that. If you accidentally have your multimeter in the amps range and now you connect it to the mains, then of course you have an extremely low impedance path where the current is only limited by the value of your current shunt, which we can see here. I think it's 150 milliohms or 50 milliohms, I can't remember. And the fuse, and you get extremely high currents, and you need special HRC fuses just to prevent your multimeter from catching fire, because arcing will start in, and it's quite difficult to extinguish an arc at such high currents in the hundreds or even thousands of amps regime. So, and you can see there are separate compartments here for example here for the 500 milliamps fuse, and we have of course our isolated 4mm banana jacks, and here we can see a whole lot of components which also have to do with protection, in this case of the volt input. So the thick fuses, they are for the amps range, but on your voltage input terminal, the problem you can get there is when the voltage becomes too high, then you need different measures just to protect your multimeter. And we can see here we have some high power, probably in the 1 or 2 watts region, power resistors. So these are not shunt resistors, because the amps range is here on this side. These are just to current limit the current in case of failure in your volts input. Then these could be spark gaps, I'm not sure. And here we have, it looks like 3 metal oxide varistors, or MOFs in short. So I will give you a link to a video from David L. Jones from the EEV blog, where he has explained all the components are just to protect the input of your multimeter. And so we have a full set here of protection components, and this is really necessary to get a Cat 3 and Cat 4 rating. So this is how it should be done. And you can also see here these little slots in the PCB. I hope you can see them. For example, here. And there are more of them here. That is also just to prevent any arcing. The slots have to have a minimum width, so that, for example, here on the MOF, you don't get any arcing from the 2 leads of the MOF. So that's how it should be done in a modern multimeter, compared to our first video with the multimeter from the early 1990s. And so let's take this further apart. Of course, everything is gold plated here, just because this is a precision multimeter with 0.02% accuracy in the volts range. And we have a little trimmer which I won't touch. So, and here where the rotary switches, they even have marked the different settings of the rotary switch. So let's continue to take this apart to see if we can get any insight into the circuit topology. So there's a little extra PCB here, apparently for the rotary switch and for the push buttons. What I don't like at this multimeter is this cheap 9-volt battery connector. These cheap ones usually don't last forever. Here it comes out. What I wonder is I can't see any shielding here on the back side. That's strange. Usually such precision multimeters have a little bit of aluminium coated cardboard or something like that to protect it from electrical fields creeping into the multimeter. Okay, here we have part of the contacts of the rotary switch and a few passive and active components. So I'll try to read the markings of these ICs. So what we can see with a little bit more of magnification is this looks like a date code, 23rd week of 2009, which could be fitting to when this thing came out. I don't know, we have a few unpopulated components like here. I don't know what this IC U8 is for. It's marked as C3E K42. It could be a voltage regulator, but I can't see any bypass capacitor, so it's probably something else. Anyway, here, this IC U5, this is an E squared prom, an S24 CSO, probably holding the calibration data of the multimeter. And this here is an HT7660, so this is the Holtec version of the ICL 7660, the venerable switched capacitor voltage doubler or inverter. And we can see the capacitors here belonging to the voltage doubling or voltage inverting. So can we see something else? A few diodes, a few transistors. Again, two unpopulated components here, but nothing very interesting. So here on the other side, that's quite interesting. The connection, the designations of the pin connectors is marked. Here we have clock and data for the E squared prom, VDD, then probably some I/O lines for the microcontroller, for the push buttons, etc. And on the other side, let's see, there's something interesting. Again, different power supply lines, like here VDD1, VREF. So I think that was it for this little daughterboard or daughter PCB. And let's see what else we have on the main PCB. So next is we get away with this rubber gasket here. This is probably also to make this thing kind of blast proof, because imagine that if one of the protection element here explodes, so fails in the end, you could get a lot of smoke and even flames, and to protect them from getting outside, that's the purpose of these extra casings here. It's not a double-walled structure, but together with the rubber gasket to prevent smoke and flames from getting outside of the multimeter. So the main PCB is somehow still fastened to the lower half of the case. The only screw I can see is this little thing here. Let's see. Yep, now it seems to come out. And here we see some of the shielding. Well, this is of course the back side. I just mixed up the other half of the multimeter, which is the front. And here we have these aluminium foil just for electrical shielding, and the little buzzer, and then we probably have spring contacts here to connect it to the buzzer here. and to the shielding. Okay, on the back side there is not a single component as far as I can see. Again, some unpopulated areas, and we already can loosen the screws here for the LCD. By the way, this the backlight for the LCD is notorious for being next to being useless, and I think I've even found somebody who modded the LED for the backlight to give a more brighter image. Are these even the LEDs here? Strange, they look like LEDs. Here you can see beautifully the gaps in the PCB to prevent any arcing over from one component or one lead of the component to the other. And here we also have two extra screws. They belong to the rotary switch, which we don't have to take off. But here the LCD came off nicely. I hope you could see that. Just came out that way. So we're getting nearer to the internal guts of the PCB, and I'll enlarge the magnification a bit so that we can see a little bit more detail. So in the meantime, I've identified a few of the missing or dubious components. So let's go again from the inputs up to the ADC. This HRC fuse is still surrounded by all in all 4 1N4007 high voltage diodes, so additional protection by the standard 4007 diodes, just as well as another one you can see here. And the path here on the voltage input is, here we have 2 power resistors, each of 1K and 2 each of 400 ohms in series. Then these things here must be PTCs because they measure 1.2 kilo ohms. And these are designated as SPG 1, 2 and 3, which probably is the abbreviation for spark gap. But these are, with 90% confidence, these are metal oxide varistors. And so basically this here is the protection for the voltage input, and this string here is for the milliamps input, and this is for the 10 amps input. Here you also can see the 1 ohm shunt resistor for the milliamps range, and this one here, I have to look it up, I think it's 65 milliohms for the 10 or 20 amps current range. So again, if you look over the PCB, there are a lot of unpopulated components. So either there was still a higher grade or a model with more functionality intended, or they simply decided, well, we don't need these extra components. So let's go on. This big capacitor here has 10 microfarads, so I'm pretty sure this is the input capacitor for AC coupling the voltages in the AC modes. Down below this here is probably the precision resistor divider. I won't take this cap off because it is soldered to the PCB. By the way it looks, so it won't be very easy. Perhaps in an afterthought, if I find it to come off relatively easily, I will give you an extra shot of what's below this. So 3 little trimmers inside. Okay, it were only 4 solder joints. So let's take off the protective shielding. And ta-da! Here is the ceramic hybrid thin or thick film precision resistor divider. The only marking there is VBM. I don't know what that stands for. And I don't know why there are 3 additional little trimmers. They know what they are doing at Brymen. And a few extra caps. So anyway, this is the precision part together with the precision reference and the precision RMS converter, at least concerning the analog part. The digital wizardry happens here in the chipset for the ADC and the LCD driver. So I won't touch this anymore because I don't want to lose the calibration. And let's put this thing back together again. And then we have a lot of op-amps which are designated 062, but from JRC, which is probably Japan Radio Corporation. So I think this is the equivalent of the TITL 062, the standard fat dual op-amps. And we can find more of them here. Here's the third one. We again have, just as in our little daughter PCB, we have here the same thing that looks like a voltage regulator because it has this 3.3 marking. It could be a 3.3 volt regulator, but I can't see any bypass caps, so perhaps one of you knows what this thing is. And this is the chipset for the main ADC, basically the brains or the main part of the multimeter. This one here is BTC AD654, and this is marked as BTC 0197-040C. So, and the interesting part is here we have the RMS converter, an analog devices AD636JHZ. So this is not the highest grade. The J version is the cheaper one. So I'm a bit disappointed that they didn't take the K version, which is twice as accurate. By the way, this 10-turn trim port is for the offset nulling. In the standard configuration, this thing here goes up to 100 kilohertz with a 1% error, or with less than 1%. If you are near the full scale voltage of 200 millivolts. I've made a separate video that the accuracy and the bandwidth of these classical analog RMS converters is very much dependent on the input voltage. So the lower the input voltage, the lower goes your frequency range. And the -3 dB point of this thing is above 1 megahertz. So this is quite a nice IC. Although I'm not sure if this was the best IC during the time when this multimeter was engineered. There could have also been already better RMS to DC converters. Anyway, they didn't take the highest grade here, but only the lower grade version. And the same is true for the precision reference that is here, also an analog devices part. It's a Rev 43G. The better specs would have been in the Rev 43F. So anyway, this thing has 2.5 volts with typically 0.04% initial accuracy and a temperature coefficient of 25 ppm per Kelvin or per degree Celsius. And I'm not sure if they are not cheating here on the specs of this thing. This thing sells with an initial DC accuracy of 0.02%. It could be that this thing is factory trimmed in software or factory calibrated in software to give you really the 0.02% accuracy. Anyway, the reference voltage here, it does not have 0.02% guaranteed accuracy. So I think that was it for a main overview of the innards of this originally Brymen and rebranded Extech multimeter, quite interesting how much effort, especially here, half of the area of the PCB is for the protection elements, and the wizardry happens here on the left half of the PCB. And here are still the LEDs for the backlight. The ones on the back side here are in fact for the infrared communication, for data logging. So the backlight LEDs are these here, and they could be exchanged for more brighter ones because the backlight is hardly visible. It's one of the worst backlights I've ever seen in a multimeter. So anyway, I think that was it for today. So thanks for watching. Until next time, bye from Roger, bye from Kanka Labs. Works again.